Hello, everyone. As promised, I will move on from Schwarzschild black holes and talk about more complex structures, namely black holes with charge and the Reissner-Nordstrom solution. So let's go. The outline of this lecture is as follows. First, I will, as always, summarize what we did in the last lecture. Then I will derive the Einstein-Maxwell equations and use the Einstein-Maxwell equations to derive the generalized Birkhoff's theorem. And finally, I will apply some boundary conditions to the solution of the generalized Birkhoff's theorem and obtain the Reissner-Nordstrom metric. Recall, in the last lecture, we assumed that the interior of a star is modeled by a perfect fluid, and the exterior is modeled by a simple vacuum. So the energy momentum tensor is simply as follows, where R less than 2m is the perfect fluid energy momentum tensor, and R greater than 2m is the vacuum energy momentum tensor. Moreover, for the metric to be physically meaningful, it has to satisfy some conditions like hydrostatic equilibrium. And as a result, the metric must be continuous at R equals 2m. And thus, we write the metric in the following form. And as mentioned before, these functions are chosen to make the expressions look nicer. You can, in principle, just make this A of R and this B of R. But they also have some physical meaning, as M of R is simply the mass of the spherical star, and phi is the gravitational potential. So by computing the Ricci tensor, we obtain equation 1.3 and 1.4. So this is the TT component, and this is the theta-theta component. The RR component can also be, in principle, computed using the Ricci tensor, but we used a neat trick. We exploited the conservation of energy and momentum and used the continuity equation to obtain equation 1.5. And by substituting equation 1.5 into equation 1.3, we yield the TOV equations. And this is an equation that relates the pressure, radius, and the mass. Now, when we calculate the TOV limit, we can make some assumptions, and the most simple model is to assume that rho has constant density. And doing so, we obtain an expression for the central pressure. And for black holes, the pressure at the center must diverge because there is a singularity, and thus the denominator is set to 0. And by doing so, we solve for the mass, and we find that it has this expression. And given that the density of a nucleon is about 5 times 10 to the 17 kilograms per meter cubed, then the TOV limit is about 3 solar masses. But we can further make this model more realistic by using a polytrope model, and we can numerically calculate the TOV limit. And by doing so, we have a TOV limit within the range of about 2.4 to 2.9 solar mass. But we can see that the constant density case is pretty damn close to the upper limit of the TOV limit of polytropes. So now let us move on to what we will discuss in this lecture. So the goal of this lecture is to derive the Reissner-Nordstrom metric. And to do so, we need to first have an equation that describes both gravitational fields and electric fields. So in general relativity, when we derive the Einstein field equations, we do it by varying the Einstein-Hilbert action. And R is the Ricci scalar, and the square root of minus g is the square root of the determinant of the metric. And this is similar to taking when we calculate areas and volumes in differential geometry, where we take the square root of the first fundamental form. But since we consider space-time, we need to take the metric. And moreover, we have to integrate over 4 spatial dimensions, namely time and the 3 temporal, the time dimension and then the 3 spatial dimensions. So to derive the Maxwell equations, we can use the Faraday tensor and have the following electromagnetic action. So recall that the Faraday tensor is simply the anti-symmetrized derivative of the 4 potential, where the 4 potential is a 4 vector, where the time component is the scalar potential and the spatial components are the vector potentials. And let me further discuss about the Einstein-Hilbert action. This is the simplest scalar that we can put in that makes sense. If we want to modify gravity a little bit, we can add extra terms like contracting the Ricci tensor with itself, or the Riemann tensor with itself, or maybe add some other tensors in there, like or maybe even add vectors in there. So we can have vector gravity, we have tensor gravity, but this is the simplest case. And those other cases is one potential way we can modify gravity to, I guess, fit some potential inconsistencies with general relativity. But as far as we know, we do not find any inconsistencies with general relativity. So this theory is sufficient currently. But the beauty of field theory is that one can couple fields by adding up the actions and applying the least action principle to obtain the combined equation of motion. And doing so, we find that the combined action is as follows. And by varying the action and using the least action principle, namely taking the variation of S, and then we set the variation to 0, we obtain the Einstein-Maxwell equations. And this equations governs the behavior of particles subjected to both gravitational and electromagnetic fields. So in lecture 1 of the black hole series, we proved Birkhoff's theorem and derived the Schawarzschild metric. And recall that Birkhoff's theorem is as follows. Basically, it states that a spherically symmetric solution to the vacuum Einstein field equations are static and asymptotically flat. We will see that the addition of a spherically symmetric electric field will not change Birkhoff's theorem and can be generalized as follows. So a spherically symmetric solution to the vacuum Einstein-Maxwell equations with a radial electric field are static and asymptotically flat. The first step in proving the generalized Birkhoff's theorem is to write the Einstein-Maxwell equation in a nicer form. Notice that the term that contributes to the electromagnetic field can be treated as an energy momentum tensor. So if we go back here, this is simply the Einstein tensor, right? But we can always write this part as the energy momentum tensor part. And one neat property of this particular energy momentum tensor is notice that it contains the Faraday tensor. But the Faraday tensor is quite nice because as we look at the expression for the Faraday tensor here, notice that if we substitute mu equals nu, we get this side is 0. So we say mu equals nu, so we get a, so partial mu, a mu minus partial mu, a mu. So this will be 0, right? So this implies that the Faraday tensor is traceless. So what does this mean? This insinuates that the energy momentum tensor is also traceless. So we can write the Einstein equations in a nice form. So usually what happens is if the energy momentum tensor is not traceless, we would have to add an additional term like 8 pi over 2 times the trace part. But here we have quite a nice equation. And the reason for writing this in this form is because the Ricci scalar is quite it's not difficult, but it's quite laborious to compute because we have to take the Ricci tensor and contract it with the inverse of the metric tensor. So this step kind of bypasses us from doing that. So recall from lecture 1, we know that a spherically symmetric metric takes the following form, and we derive this using coordinate transformations. Moreover, we calculated the Ricci tensor components using 2 different methods. The first of which is using the Lagrangian method, which is also quite difficult because we have to, the Lagrangian method only calculates the Christoffel symbols, and we have to substitute these Christoffel symbols into the definition of the Ricci tensor. The other method is a little bit more, I guess, well, I wouldn't say it's more direct, but we're calculating the Ricci tensor in orthonormal bases. And we are subtly calculating the Christoffel symbols, but we do it in a more direct manner using Cartan's first and second formula. So I will not do these calculations again. If you want to see how these calculations are done, refer back to lecture 1. So these are the Ricci tensor components for this spherically symmetric metric. And to prove that a spherically, so first, let us prove the first part of Birkhoff's theorem. So we will prove that a spherically symmetric solution to the vacuum Einstein-Maxwell equations with a radial electric field are static. So basically has no time dependence. To do so, we need to calculate the energy momentum tensor components first. When we assume a radial electric field, we need so the only non-vanishing components of the electromagnetic tensor are the FTR components and the FRT components. And the reason for this negative sign here is that notice, since that the Faraday tensor is the anti-symmetrized derivative of the 4 potential, if we swap the indices, we simply get the negative part of the Faraday tensor. So basically, in other words, the Faraday tensor is anti-symmetric. So if we set the FTR term to be some electric field that is only dependent on the radial coordinate and the time coordinate, then this is a radial electric field. So now let us compute these two terms. And the reason why we want to compute these two terms is quite simple. It's because they are involved in the energy momentum tensor term. So this term is, so we can see these two terms. And by assuming that the electric field is radial, we can get quite a nice expression. So here, since the electric field is radial, there's only the mu t and the r and the mu r components, right? But recall that when we have repeated indices, we need to sum over all indices. So let us do that first. So let us sum over the index. So let's sum over the r index. So this will be non-zero, but this will be 0 because the r component is 0. And we need to sum over the t index. So t is also 0, and this is non-zero. So we need to add 2 of these components together to get this equation. So we get a half g mu nu is equal to this component. So similarly, we can do, we need to compute this component, which is right here. So doing so, we get this equation because all the other components vanish, and we get a nice expression for the energy momentum tensor. Therefore, the non-vanishing components of the energy momentum tensor are as follows. Now, notice that the TR component of the energy momentum tensor is 0. And since the energy momentum tensor must be symmetric, then the TRT component is also 0. This implies that the RTR component is 0. And since the Ricci tensor is also symmetric, we can just swap these two and this will also be 0. Similar to the Schawarzschild case, we get this equation, right? So since we get this, this implies that B dot is 0, and thus B is purely a function of R. Moreover, from the first lecture, we also have this expression. So A over B R plus RTT is the same thing as the, well, it's the same thing as A over B TRR plus TTT, right? So this, if we have a different energy momentum tensor, this need not be 0. But in this case, we do see it, in this case, we do see it 0, right? Because these two are very, very similar. We just take A over B and we get 0. So we get this equation. And from this, we get the following differential equation, right? So which implies that A is equal to G of T over B. So some arbitrary function of time over B. And from this, one can show that the FTR component is equal to A times B over F superscript. So basically to get this, so to raise the index, we have to multiply it by the inverse of the metric. And the inverse of the metric here is just AB. So and AB is just simply G of T. So we get this nice expression. And from here, to make progress, we need to solve the Maxwell equations, namely this one. So if there were basically 4 currents, this will be 4 pi J nu. So, but since we're considering the vacuum case, this is 0. And this other equation can be obtained by the Bianchi identity. And I did discuss this in my lecture on optics that I've already released. So I guess you should be somewhat familiar with these two equations. And with the benefit of hindsight, we know that equation 3.20 yields no new information because, well, we know that this component is 0, right? So these two are, basically we have these two equations. I think there's a mistake here. This should be a plus sign, but basically this will be minus, and then we swap these two. So this will eventually equal 0. So this is a trivial solution. So basically this right-hand side is 0, and this is 0. So we get 0 equals 0. There's a trivial solution. It yields no new information. So therefore, we will use equation 3.19. So we just take the covariant derivative of the Faraday tensor. And since all these components are 0, so these ones are equal to 0, therefore, we get that the partial derivative with respect to t of the Faraday tensor is also equal to 0. And since this is the electric field component, what we can do is just, so since the partial derivative of a supposedly time-dependent and radial-dependent electric field is 0, this implies that the electric field has no time dependence. So now we want to compute this expression. And the second term vanishes. You can show this. This is quite easy to show. I will not do it here. You can do it as an exercise yourself. But the third term is more interesting because what we'll see is that since we have a relationship between A and B, we know that this is 0. So we get two, the only non-zero term is a 2 over r term. So by doing this, we get the following equation. And since this is a partial derivative with respect to r, right? So the general solution is we can integrate both sides. Yeah, we can integrate both sides with respect to. So yeah, since f of r is some so basically we just solve this differential equation, right? So we get this expression here. So we get f of t is, so we get ftr is equal to some arbitrary function over r squared. But we did prove before, right here, that frt and ftr are both time independent. So thus we know that ft must be a constant. Now, recall that Gauss's law states that the surface integral of the electric field is equal to 4 pi times the enclosed charge. And for a sphere, since the area is 4 pi r squared, we cancel the 4 pi's, we get the electric field in the radial direction is q over r squared. And thus, to match the boundary conditions, we know that this constant here must be, so this constant here must simply be q. And now we are ready to solve the Einstein equations. So we have to compute the r theta theta component. And we have to equate this to 8 pi times t theta theta. And doing so, we get this expression, right? This is quite an ugly differential equation, but we can rewrite it in a nicer expression. We can rewrite it like this, right? So if we can rewrite this term as partial r of r over b, we can just, I guess what we can do is we can subtract one side by the other and just rearrange the equation to get 1 over b is equal to g of t plus h of t over r plus q squared over r squared. So this is the general solution, right? So this implies that b is equal to this and a is equal to this. But recall that b dot is equal to 0. That means b has no explicit time dependence. So g of t must be 0. Sorry, not 0. G of t must be constant, and h of t must be also constant. So that means we have shown that b is equal to this, excuse me, and a is equal to this. And by looking at these two equations, right, we can simply set r to infinity, and we see that these two do not diverge. If we set r to infinity, this becomes 1. Set r to infinity here, this becomes C1. So the solution is asymptotically flat. Therefore, we have successfully proved the first part of the generalized Birkhoff's theorem. Actually, we've proved not only the first part, we've proven the whole Birkhoff's theorem. We've already proved that it's static, and we've proved that it's asymptotically flat. So my mistake, we've proved all of the generalized Birkhoff's theorem. And now we can derive the Reissner-Nordstrom metric. And to do so, before I do so, there's something interesting about the Reissner-Nordström metric. The Reissner-Nordstrom metric, like in the Schawarzschild case, the metric is another example of black hole uniqueness theorems. And here, the resultant, basically, the resultant metric is a unique solution to the vacuum Einstein field equations. And once again, the proof of such is quite involved. But if you want to learn more, please feel free to do so. Read chapter 5 of Heusler's black hole uniqueness theorem books. And using the uniqueness theorem, we can prove the converse of Birkhoff's theorem, that is an asymptotically flat and that asymptotic flatness and time independence implies that the metric is spherically symmetric and must satisfy the vacuum Einstein-Maxwell equations. Now, to derive the metric for a charged black hole, in other words, to solve for C1 and C2, we can use a boundary condition. Recall, the Schwarzschild metric is as follows. And since E sub r is the electric field, one can infer that when we set Q to 0, if there is no electric field, then the Einstein-Maxwell equation should reduce to the Schwarzschild solution. Thus, so let's go back here, right? We set Q to 0 and Q to 0 here. So here, this implies that C1 must be equal to 1 and C2 must be equal to minus 2m. And thus, the spherically symmetric solution to the vacuum Einstein-Maxwell equation is as follows. And this is the famous Reissner-Nordstrom metric. The physical interpretation of this is quite simple. The contribution of the electric field part is simply that of a point charge, and this can be interpreted as a black hole with a point charge at the center. But I must state there is a minor disappointment about charged black holes, as they are not really astrophysical. This is because if a black hole has either a positive or negative net charge, the electromagnetic attraction combined with the gravitational force will quickly accrete matter of the opposite charge and make the black hole neutrally charged. However, that is not to say that charged black holes are not worth studying, as they do have a lot of interesting mathematical properties, and they also have connections to theories like supergravity and string theory, which I may discuss. So supergravity I will discuss when I talk about the Majumdar-Papapeter solution, and I will further discuss supergravity when we talk about when I explicitly prove the positive energy theorem, but that will be a couple lectures away. So I hope that you've learned something from this lecture, and next time I will talk about the Eddington-Finkelstein coordinates for the Reissner-Nordstrom metric, or the null cores for the Reissner-Nordstrom metric, and how we can get Finkelstein diagrams to describe the radial null geodesics in Reissner-Nordstrom spacetime. So thank you.